In this video, we'll learn about an array, what is an array, and how to declare an array and initialize an array. Then, what are the methods of accessing elements of an array? So, let us start with introduction to an array. Before talking about arrays, let me explain about simple variables. So variables are supported by every programming language, and the variables will have some data type. For example, if I declare a variable of type integer and whose name is x, and in this I want to store the value 10, then we know very well that at runtime variable x will get some memory. If we assume that integer takes 2 bytes, then 2 bytes of memory will be allocated for x. Let us say first byte address is 100, then the next byte address is 101, and together in these 2 bytes the value 10 will be stored. This we are already familiar with. So this type of variable is a single valued variable which can store just one single value. And this single valued variable we can also call it as scalar variable. So this is a scalar variable. Scalar means which is having just magnitude. So this is magnitude, the value is 10. That's all. Then what is an array? We can store multiple values, that is list of values or say set of values. So array is a collection of elements and all the elements are of same type. So array is a collection of similar data elements grouped under one name. Suppose instead of just one value, if I have to store list of values, then I can declare an array. Let us say integer type array I want, and the name is A and the size is 5. So this will give me an array of size 5 where I can store 5 integers. 5 integers I can store, and the indices 0, 1, 2, 3, 4. Now here this is a scalar variable where I can store just one value. This is a vector variable which is also having a dimension. It's a single dimension. So I can store total 5 values in this one. So we can call this variable as a vector variable. So arrays are vector variable. This is a single integer under name x. These are 5 integers under name A. The memory allocated is 100 and 101. For 5 integers, total 10 bytes of memory will be allocated if the integer is taking 2 bytes. For example, the first byte address is 200, then the next byte is 201, so this is 202 and 3, 204 and 5, 206 and 7, 208 and 9. So the memory allocated will be contiguously. So all the locations will be side by side. They are contiguous. For 5 integers, total 10 bytes of memory is allocated together as a single block. Now all those 5 integers are having same name, that is A. Then how to differentiate those 5 integers? We can differentiate them with their indices. Now A of 0 means this is first integer, second integer, third and fourth and fifth. So I can access them or differentiate them with the help of index. Suppose I want to store a value 15 here. Then I can say A of 2, that is index 2, assign value 15. So this will store the value 15 here. So using the name and the index, we can access any of those integers, any of those elements. So that's how array is a collection of elements or a list of elements which are of same type or are of type integer, and this is supported by every programming language as a basic feature of a language. This is there in C language as well as C++. Now let us see what are the different methods of declaration and what are the various ways of initializing a array. First method is, if I am declaring an array with the name A of size 5, then this will allocate the memory space for 5 integers. Indices are 0 to 4, and this is just a declaration. So the values inside this one will be garbage values because nothing is initialized, so the values will be garbage. Means unknown values, random values will be there that are not initialized by us, so they are not useful for us. So we say garbage values. Now next method, if I want to initialize the values, then I should say this is a part of declaration, and here I can initialize the values like 2, 4, 6, 8 and 10. Suppose I am initializing also, then an array will be created during runtime and all the values will be initialized in this one. So this looks like 2, 4, 6, 8 and 10. This is the second method. So this is the declaration plus initialization. So if you want to have some values initially in an array, then you can mention all the values. Now third method, you can mention the size, but if you don't want to initialize all the values, just few values you want to initialize, then an array of size 5 will be created with the indices 0 to 4. As only two values are mentioned, so only 2, 4 will be initialized and the remaining elements will be initialized with 0. Because once the initialization process starts, it will try to initialize all the elements. So remaining values are not given, so it will initialize them with 0. So even I can say like this, integer a of size 5 and just 0. Then this will create an array and initialize first one with 0, as it will continue initializing rest of them also. So it will initialize all of them with zeros. Then one more method is there for creating an array. Just you can mention the values 2, 4, 6, 8 and 10. Then depending on the number of elements you have mentioned in the initialization list, the array size will be same as that one. So an array of this 5 size will be created and it will be initialized with all these elements. So if I add one more element to this one, like let's say 12, then total size is 1, 2, 3, 4, 5, 6. So array of size 6 will be created and this will be initialized with these elements. So these are the various ways of declaration and initialization of an array. This is there in both C as well as C++. If you write like this inside the program, then during runtime, this is how it will work inside the main memory. Now next we will see how we can access all the elements of an array. Here I have an array of size 5 which is already initialized with these elements. So during runtime, the array will be created like this and the elements will be stored in these locations and their addresses also I have mentioned. The addresses will be contiguous. Now, how to access those elements? So if I want to print any value, so I can say printf. Suppose I want to print a value that is at index 0. So then I can say %d a of 0. This will print the value at index 0. Suppose I want to print the value 1, then I should make it as 1. So it means I can access all those values by just changing the index. A of 1, A of 2, A of 3, anything. Now if I have to traverse through an array, so traversing means visiting all the elements once. So if I have to traverse all the elements, then I can take the help of for loop, which will help me change these indices from 0 to 4. So this can be changing from 0 to 4. So first time 0, this will be the element, then next 1, then 2, then 3, then 4. So it will allow me to access all the elements by traversing through those elements. So for loop is used for accessing the elements in an array. So for I assign 0, I is less than 5 and I plus plus, and here I can mention I. Now I can access all those elements. So for loop is used for traversing through all the elements of an array. And the element can be accessed with the name of an array and the index. Now next let us see what are the ways of accessing a particular element in an array. If I want to print this element, then I can say printf %d a of 2. This is one method. Then the same thing, printf, I can even say 2 of a. This is another method. So even you can use index outside and the name of an array inside subscript. Then using the pointer arithmetic also we can access that elements, that same element if I want to access, then printf so and so, I can say star a plus 2. This plus 2 must be inside the bracket. Star must be for entire thing, that is a plus 2. So I can mention any index here and I can write star here and I can access that particular location. So array elements can be accessed by using the subscript, that is index, as well as they can be accessed with the help of pointer arithmetic. So these were all the basic things about an array. So we'll learn more about arrays in the next video. In this video, we will look at the demonstration of declaration and initialization of arrays. We have already seen in previous video, there are various methods of declaration and initialization. So we'll try all of them here. First method, declare an array of some size. I have declared an array of size 5 and I am not initializing it. Next, I will declare an array of some size 5 and also I will initialize values. I have initialized 5 values. Third method, I will declare an array of size 10 but I will initialize only few values. I have initialized only 3, remaining 7 values will be made as zeros. Then next, I will declare an array of size 5 and I will assign only 0. Then as the first element is 0, the rest of the elements will also be filled with zeros. Then one more method, I will not mention any size, I will write down the elements. I have given 6 elements. Now here I write return 0. I'll put a bookmark here. See, I'm getting here warnings that all these variables, I'm not using them anywhere in the program. So if the variables are not used, then compiler is giving a warning. So the warnings are instant and the errors are also, you have observed, they are instant. So that is the benefit of using this editor, this Xcode IDE. I will run the program and show you how these arrays are created in the memory. I'll put a breakpoint here. Then I will run the program. Here you can see in the debug area, that is in a watch, all the variables are shown here. A is of size 5 and all these values are 0 and the last value is some garbage. So actually these zeros are also garbage. It can be any number. Now next array, if you look at, it is filled with values 1 to 5. So here we have initialized array with 1 to 5. I'll close them. Now next array C, I have taken an array of size 10 but I have initialized only 3 numbers. Rest of the numbers will be zeros. Automatically they are initialized with 0, they are not garbage. And the D, all are initialized with 0, there is no garbage value here. These are the values that we have initialized them. And E, you can see I have not mentioned the size, but I have given 6 numbers here. So an array of size 6 is created. It is showing an array of size here inside this bracket, and there are 6 elements 0 through 5. I'll stop this. I will remove these declarations and I will show you how the addresses of array locations are contiguous. I will print the addresses of array A. So for that I need a for loop. So using for loop, here I will print the addresses of all the locations. So for printing addresses, I should use %u and space, new line. Then I will print the address of A of I. Ampersand will print the address. So for printing addresses, I should use u. I'll remove the breakpoint. Now let us run the program. See, these are the addresses of all the locations. There are total 5 locations. So first address, that is first integer address, is 56, and here the integer is taking 4 bytes. So plus 4 is 60, the next plus 4 is 64, the next plus 4 is 68, the next plus 4 is 72. So all these addresses are contiguous. All the location, that is A0 to A4, the locations are side by side, and in this compiler integer is taking 4 bytes. But when I am discussing on whiteboard, I am assuming that integer is taking 2 bytes, so that is easy for me for explaining the things. So that's all in this video. We have seen how we can declare and initialize arrays. Now let us look at static versus dynamic array. So static array means the size of an array is static, and the dynamic array, the size of an array is dynamic. See, once an array is created, its size cannot be modified. So in our programs, when we declare an array, for example, I have a function void main, and inside this function, if I have declared an array integer of size a 5, then array of size of 5 will be created. So the question is where it is created. As it is mentioned inside the main function as a variable, just a vector variable, then the memory for this array will be created inside stack. So an array of size 5 will be created inside the main memory as a part of activation record of main function. So this array will be created inside stack. So why I am calling it as static? Because the size of this array was decided at compile time. Though the memory will be allocated during runtime only, memory cannot be allocated at compile time. So memory will be allocated during runtime, and the size of that memory was decided already at the compilation time. Definitely the size of an array has to be decided at compile time in C language. In C language, when you are mentioning the size of an array, it must be a constant value. It cannot be a variable. It must be a constant. So you must write some constant value there. But in C++, we can create an array of any size at runtime. So at runtime, a size of an array can be decided and it will be created inside the stack only. Whereas in C language, the size has to be decided at compile time only for the arrays inside the stack. Let us see in C++, suppose I have one variable n and C in n. So it means I am reading some input from the keyboard, the size of array as n. Then I can declare an array of some size n. So whatever the input comes from the keyboard, I can create an array of that particular size. So size of an array is decided at runtime. You can enter any value in n at runtime. So an array of that size will be created inside the stack. So size of an array can be decided at runtime in C++, but in C language it has to be mentioned at compile time only. This is the difference. And both these arrays are created inside the stack only. So there is no space to show you B also. So assume that B is also created inside the stack. So this part is in C language, and in C++ this is also allowed. Now next, we will learn how to create an array inside heap. So whose size and the type, everything is decided at runtime. Now one thing you remember, for accessing anything from heap, we must have a pointer. So first of all, I should declare a pointer. So I will declare the name of a pointer as a p. This is a pointer. Now where this p will get the memory? As a is a variable of type array, p is also a variable, so this will also get the memory inside stack. Now remember, in any language, when you declare a variable, the memory for that variable will go inside the stack only. Then when it will be allocated in heap, let us see. Now that pointer, I will use it for creating memory in heap. So then I should say p assign new int of size 5. Then the memory for 5 integers will be created inside heap, and this pointer p will be pointing onto that address. Suppose the beginning address of this contiguous memory is 500, assume that, then 500 will be stored in this pointer. So now the program can access that heap by coming onto the pointer and taking the address, and it can go there and access it. So heap memory cannot be accessed directly, it has to be accessed indirectly. Now one important thing I have to show you here, when you get the memory from heap, whenever you say new, then only you get the memory from heap. Otherwise, all the variables, whatever the variables you declare, they will get the memory inside the stack only. Now new is a operator that is in C++, then how to create the same thing inside C? So for that, I have to say function malloc or malloc function, and I should mention the size. So I want 5 integers, so 5 into, now size of an integer, it may be 2 bytes or 4 bytes, depends on the system or the compiler. So I should mention here size of int. So this is the common practice that is done in C language. Instead of mentioning 2 bytes, we mention size of, so that depending on the system or compiler, it takes that size. Then malloc function will allocate just a raw memory, just the block of memory. Now that memory we want to use it as integer, so we have to typecast it as integer pointer. So this is in C language and this is in C++. New is the operator used in C++ and malloc function is used in C language. So once again, when you declare a normal array, then it will be created inside stack. When you want an array in heap, then you must have a pointer and then you should allocate the memory either using new operator or using malloc function. It will be created in heap, and the heap memory can be accessed indirectly with the help of pointer. Now one more important thing. When we have allocated the memory in heap and after some time during the execution of program, at any stage, if that memory is not required, then you must delete the memory also. If you don't delete the memory, unused memory, then it causes memory leak problem. If the unused memory is not released, then it causes memory leak problem. So how to release the memory? In C++, we have to say delete P, but P is used for an array, so it must be mentioned here as a subscript. And in C language, say free P. So this is the method of deallocation in C++, and this is the method of deallocation in C language. So I have shown you the syntax for both the languages. So the main concern here is how to get the array inside heap. Now next we will see how to access that array from heap. And this is a normal array inside the stack and this is an array inside heap. Now how we access this normal array inside the stack? So for accessing any location, I should say a of 0 assign 5. So the value 5 will be stored here. Now same thing I can say P of 0 assign 5, just like a normal array, I can access this also, so the value 5 will be stored here. So it is as simple as accessing an array inside the stack. You can access an array from heap by using a pointer. So pointer acts as a name of a array. So already we have learned that this entire array can be accessed with the help of a loop, for loop. Then that array can also be accessed with the help of a loop. As we saw that this can be accessed using pointer arithmetic, so even that can be accessed using pointer arithmetic. So we don't have to relearn that thing, we already know it. Now the next important thing here is that wherever you create an array, whether you create it inside stack or you create it inside heap, once the array of some size is created, it cannot be resized. Its size cannot be changed. If at all you want to increase the size of an array, it is possible in another way, but it is possible only in heap. Stack array cannot be resized at all. But a heap array, same array cannot be resized, but we have some alternative for that. So let us learn how we can increase or decrease the size of an array. In this video, we will see what the methods of creating array, that is in a stack, static array, or inside heap. We have already seen this. We can create an array by just mentioning the size. So this array will be created inside stack. Next, for creating an array in heap, we must have a pointer. To that pointer, we can create an array in heap and assign the address of that array to that pointer. So here I will write on the code p assign. For allocating memory in heap, the function is malloc function. And suppose I want to create 5 integers, so we know that so 5 into size of integer. We can use an operator size of integer because here in this compiler it is taking 4 bytes. So whatever the number of bytes a compiler is taking, it will take that many bytes. This malloc function will return void type of pointer, so it must be typecasted before use. So I will typecast it as integer type. This will create an array in heap. Here I will change the array size to 5 and I will initialize with some numbers 2, 4, 6, 8 and 10. Now this array what I have created just now using heap, I will initialize this array, that is p of 0 with 3. I will assign odd numbers. Now here I will take one integer variable for displaying the values. So I will display the values of array A as well as array P using for loop. So first for loop I will print the array A. Yeah, with the for loop I am printing all the elements of array A from 0 to 4. Same for loop I will copy here to print the dynamic array that is pointed by P. So I will write P of I here. Between these two I just want a new line, so printf/n, so their results are displayed one after another. Next thing is I am getting a warning here that's unable to find the definition of malloc function, so for that I should include a header file, that is stdlib.h. This function is available in stdlib.h, so this is gone. I will run the program and show you. These are the two for loops used for printing the values of array A and array P to confirm really the arrays are created and they are holding those values. Yeah, you can see that 2, 4, 6, 8 are the values that are kept in array A, and 3, 5, 7, 9, 11, these are the values that I have assigned them to array P. So in our programs, wherever we want to allocate array in heap, then this is the method using malloc function you can allocate memory in heap. I will put a breakpoint here and debug the program and show you. So here is a breakpoint on the return statement, then I will run the program. Let us see how these arrays looks like. See, this array A is having values 2, 4, 7, 8. Array is having values 2, 4, 6, 8, 10 and it is of size 5. So here in the brackets you can size 5. Then P is just a pointer, it's not an array. And this pointer is having so and so address. This is the address. Then P is pointing on the first element. As I have shown you on the board, whiteboard, that pointer will be pointing on the first element, but using that pointer you can access all other elements. So this is P of 0, that is 3. And plus 1, if you say you can access this one, or P of 2, P of 3, P of 4, we can access all these elements with the help of this pointer. So it's showing only one value when it is dereferenced. So star P gives value 3. The address of the array in heap is given here in the hexadecimal form. This is the hexadecimal number. So that's all. This is the demonstration of creating array in stack as well as in heap. Here already I have an array of size 5 that is created in heap and pointer is pointing to that array. So this is a pointer P and this is in stack, this is in heap. We know very well now. So this is pointing there. Suppose already it is having some elements. That size 5 is not sufficient for me. I want a larger size array. Then one method for increasing the size is take one more pointer, that is call it as Q, and create a new array of required larger size. Let us say I want an array of size 10. Then pointer Q will be pointing upon an array with a larger size 0, 1, 2, 3, so on. Now this Q is pointing on a larger size array. So I cannot increase the size of the same array. Already I said that. So alternate is create a bigger size array. Now transfer all those elements from P to Q. So we know the size of P very well, that is size is 5. So for I assign 0, I is less than 5, I plus plus. Then in Q of I, copy the elements of P of I. So I'm copying them using for loop. So all these values will be copied here. 5, 8, 9, 6, 4. So the values are copied there. And even there is one function in C language that is called as mem copy, that is memory copy. You can use that and mention these two arrays. So those contents will be copied here. So using for loop I am showing them. Next, we want to increase the size of this P. Actually P is a pointer. P is pointing on so and so array now. Now you have to make this P point on this one. But before making P point on that one, let us delete that array. So here say delete P. As I said, if you don't delete unused memory, then it will cause memory leak. Means the shortage of memory, reduction in the size of the memory. So it is unused now. We don't need now. So delete that one. So this memory is deleted. Then make P point on Q. So wherever Q is pointing, P will also point to there. So now new location where P is pointing is this one. Then now this array is pointed by both P as well as Q. Now let us remove Q from there. Q assign null. So Q will no more point on that one. This is null. So this is not pointing on this one. It's pointing on this P. Now if I say P, this is the array now. That array is gone. It is deleted. So it is removed from the memory. And P array size is now 10. Now let us take the example like this. Like the P was pointing on this array. So P is having car. Now P is having a small car. Now that car is not sufficient. P needs a bigger size car. So P purchases a new car. So Q helped in purchasing a new car. Now P was having both the cars at that time. Then all these things are transferred in a new car and that car is sold out. Now P is owning this car. So for shifting from one car to another car, Q has helped because P has to sell away that car also. Or else you can take the example, this room is not sufficient for conducting a class. The students are growing in number. We need a bigger room. So we cannot increase the size of the current room. So we have to shift to a new bigger room. So this is a new bigger room. And all the students from that class are moved to this class. And there is a lot of free space for more students to sit in the class. So that's the idea followed for increasing the size of an array. So if you are not doing it, if some API is doing it inside programming, then definitely it is following this method because the same size array cannot be grown. Now I'll tell you the reason why the array size cannot be grown, because the memory for the array should be contiguous. For example, the beginning address of this is 500 and 501, then this should be 2, 3, 4, 5, 6, 7, 8, 9, then the next location must be 10, 11. Now we don't know whether that location is freely available or not, or it is used by some other object inside the same program. So there is no guarantee that the next consecutive locations are free or not. If the consecutive locations are not free, then the array cannot be increased. That is the reason we say that array size cannot be increased. So rather than that, we will have another larger array and shift the elements. So this is about static and dynamic array. In this video, we will see how we can increase the size of an array when it is created inside heap. So for that, I will take one pointer P as well as I will keep ready one pointer Q. First of all, using P, I will create a array of size 5. So already we have seen how to create an array inside heap. Using P, I will create an array inside heap. Using malloc function, already we have seen how to do that. Malloc and of size 5, size of integer. So this will create an array of size 5. Now in that P array, directly I will fill up the values. I will insert odd numbers. P of 0 assign 3, then P of 1 assign 5. Likewise, I will fill up all of them. Now we'll display that array P. So for that I will take one variable I for running a for loop. Here I will print all the values of an array P just to confirm the values are stored in an array I less than 5, I plus plus. Now printf percentile D, then next line I'll print the values from P of I. So this should print all the values from 0 to 4, that is 3 to 11. Let us run the program. Yes, I got the values from 3 to 11. Now suppose this array size 5 is not sufficient and I want a larger array, then same P I cannot extend its size, then I should take another pointer, that is Q. With the help of another pointer I should create an array of larger size. So here I will create an array of larger size, malloc. I will create an array of size 10, so size of integer. So Q will allocate memory in heap for an array of size 10. Now the values are already there inside P array. Those values I want them to be transferred to Q. So using a for loop I can do this. For I assign 0, I is less than 5, I plus plus. Then in Q of I should copy the values from P of I. This will copy all the elements to Q. Now this for loop that is used for printing the elements from P, I will just change it to Q. So let us see whether the elements are copied in Q or not. I will run the program. I should get all the elements that are 3, 5, 7, 9, 11 that are copied in Q also. Those elements should be printed. Yes, I am getting those elements. Now after copying at this line, I will say P assign Q. Now P is pointing on Q. And I will make Q as null, that Q array, that Q pointer is made as null, so Q is not pointing anywhere. See, right now Q is not pointing anywhere, but if I try to print the array that is pointed by Q, then see what happens. I got an error because Q is null pointer. So here inside the debug area you can see that Q is null right now and P is pointing on some other location. So I cannot use Q now. Now let us print the values using P. Yes, the values are printed. But one thing we have missed that P array before P is pointing on Q, P should delete that previous array. So for deleting, free P. So after freeing that memory, P should point on Q, then Q should be made as null. Then I can access the array of size 10 with the help of Q pointer. So though I don't have extra values, I have only 5 values stored in a new array also. So I am displaying only 5 elements. Let us put a breakpoint here in the beginning of the program and debug this program. So let us trace it line by line and see how things are working. Now P is pointer pointing to a address that is last 3 digits. If you look into this debug area, that is watch, pointer P is having address ending with 4F8. So it is pointing on this address. Right now pointer is garbage. It's not having any address, valid address, because this statement of creating of memory from heap is not yet executed. Let us continue execution. Now you can see that pointer P is pointing at an address that is ending with 9B0. I'll continue. Now Q is null right now. Q is null. So Q is not pointing anywhere. Continue. Now Q is pointing at an address ending with 470. And the value present at the first address where Q is pointing is 0. And the P is pointing at an address where the value is 3. Because we have initialized this value 3. Q is just now created using this statement. So Q is having new address, but there are no values. Now let us run this loop. The values are being copied. Now you can see that Q is also having the first value, that is 3, and the address of Q, you remember, that is 470. That is 470, and the P is 9B0. Now it is at this line, that is free P. Let us finish this line. So P is gone. The address is same in P, but that address is invalid because the memory is already deallocated. Now next line, this is very important line. P assign Q. So the address of Q will be given to P. That is 470 will be given to P. Yes, P is having address 470 and Q is also having address 470. Now next line, Q becomes null and P is still pointing on the same address. So P is pointing on a new array. So when I print these values, they are printed using pointer P. So that's all. I have demonstrated how a array size can be increased. I have written the code and I have shown you. See, I have done board work, and that same board work I have given a demonstration of that one. See, whatever we saw on whiteboard, that same thing I have demonstrated and I have shown you. Now, wherever you require, you have to follow these steps for increasing the size of an array. That's all in this video. Now let's talk about two-dimensional array. See, already in the previous video we have seen a single dimension array. In programming languages, we can have multi-dimension arrays. So basically we use one dimension or two dimension, or at most we go for 3 dimension, but languages allow us to declare n dimension arrays. So commonly used second one is 2D array. This is mostly useful for implementing matrices or for tabular data. Now let us see how to create a two-dimensional array in C and C++. There are 3 methods of creating a two-dimensional array. So let us look at them. First method is a normal declaration of a two-dimension array along with name of an array, data type of an array, and dimensions. Let us say I want an array of size 3 by 4. So we visualize that an array of 3 by 4 size will be created inside main memory with 3 rows and 4 columns. The indices will be 0, 1, 2 for rows and 0, 1, 2, 3 for columns. We represent a two-dimensional array in rectangular form, that is like a box. But really the memory allocated will be linear. For example, if you want to look at the addresses, let us assume that the first byte's address is 200 and 201. Then this is 2 and 3, 4 and 5, 6 and 7. So this is memory for each integer. As we are assuming that integer take 2 bytes, so 2 bytes for each. This is 206 and 7, and this will be 8 and 9, 10 and 11, 12 and 13. So this means that in real, the memory will be allocated like a single dimension array with 3 into 4, 12 integers. So memory will be allocated like a single dimension array, but the compilers allow us to access that single dimensional array as a 2D array with a row number and column number. So any location if you want to access, then we can say A of, let us suppose here I want to write value 15, then I can say A of 1, 2, this is 1, row number, 2, column number, value 15. So we can access 2D array with the 2 indices, that is a row number and column number. How compiler will allow us to access as a 2 dimension, though inside the main memory is single dimension, we will learn it in the coming videos. So if we want to initialize this 2D array, then we can directly mention the list of elements here, like 3 rows and 4 columns. So first row is having 4 elements, 1, 2, 3, 4, and the second row is having elements 2, 4, 6, 8, 4 elements are there, and third row is having the elements 3, 5, 7, 9. So a 2D array will be initialized. So declaration and initialize, this is common in C and C++, the same syntax is used, and the array will be created inside stack because it is just like a variable. There is no new operator used. So once you use new operator, then only the array will be created in heap. So this is the first method of creating an array inside stack. Now let us look at second method, how we can create a two-dimensional array. We can take an array of pointers. So this is a pointer and this is an array of size 3. So suppose I want the same size 3 by 4. So I have taken array of size 3. As this is an array, so normal variable, it will be created inside stack. But this is not an array of integers. This is an array of integer pointers. So I will draw that picture for that one. So this A will be created like this. And these are all pointers. So this is index 0, index 1 and index 2. Now I have just a array of 3 pointers. Now where is two-dimensional array? So I will create two-dimensional array in heap. So what actually I want? I want an array of size 4 so that this pointer is pointing there. Then again an array of size 4. Now again an array of size 4. So I should have 3 arrays of size 4 created in heap. So this is nothing but array of arrays. So there are 3 arrays and I have this array pointing to those 3 arrays, and together they form same two-dimensional array. So this is the second method of creating two-dimensional array. Let us see the syntax how I can create these arrays. So I have an array of size 3. So continuation of this one, I should say a of 0 assign new int of size 4. So an array of size 4 will be created whose address will be stored in a of 0. Similarly, I should do it for a of 1 assign new int of size 4, and I should do it for next location a of 2 assign new int of size 4. So I should create memory in heap for all those 3 arrays, and this array will be present in the stack, so it will be pointing there. Now even this structure I can access just like a normal array. Suppose I want to store a value here 15 1, 2, then I can say that array A, which is the pointer, A of 1 means this one, it's a 2 means this one. I can store value 15. So in the same way I can access it. So these were the 2 methods. Now I'll show you third method. But now let us look at third method. See, third method, I can take a double pointer. See, one was a two-dimensional array directly inside the stack. Now this is an array of pointers inside the stack, but actual arrays in the heap. Now almost everything in heap now. So for that, I will use double pointer. So declaration of double pointer, integer star star a, asterisk asterisk a. So this a is a pointer, double pointer, and this is like a variable. There is no new operator here, new is not used, so this will be created inside stack. Now I need this array as well as these arrays. So for this first array, I should say a assign new integer of size 3. I am creating this array. So you remember this array was nothing but array of integer pointers. So yes, I should mention star here. So this is an array of pointers of type integer. So an array of pointers of type integer will be created of size 3, and this will be pointing on this one. So if I take the indices, these are 0, 1 and 2. So this itself is created in heap now. Array of pointers is created in heap. Now I will prepare other arrays. So I have to create these 3 arrays and assign them to these 3 pointers. So the indices are 0 to 3, Now, how to create those three? So, same method as I did here, I should say a of 0 assign new int of size 4. Then a of 1, a of 2 assign new. So that's all. The entire structure is in heap now. Only this double pointer is inside stack because this is new, this is new, this is new. So this is created with new and all three are created with new. Everything is in heap. So that's all. These are three methods. So these are the three methods of creating a two-dimensional array. Completely inside the stack, partial in the stack, partial in heap, everything in heap now. Now one more thing. See, every time I have used new operator. So if you want to know how it is done in C language, then you know very well that malloc function is used for allocating the memory. So wherever we have used new, we have to use malloc function there. Because in C language, malloc means memory in heap. Now last thing, how to access this two-dimensional arrays. These two-dimensional arrays can be accessed using nested to for loops. So for accessing this array or any of these arrays, I can use indices I, let us say starts from 0, I less than 3 because there are 3 rows, and next one more inner for loop, j assigns 0, j is less than 4 because there are 4 columns, j plus plus. So in all my examples, I have taken 3 rows and 4 columns. So 3 rows and 4 columns. So accessing all these elements, so I can say a of I, j, whatever I want to do here. Whether I want to print them or modify them or initialize them, whatever I want to do, I can do it. But this will help me traverse through all the elements in a two-dimensional array, row by row. So it will access like this. First this element, next. Then it will come to next row, all the elements in a row. Then next, all the elements in a row. Now for accessing all the elements in a row, this is the loop. For different rows, changing the rows, this is the loop. Outer loop is there. So that's all. These are the few basic things that one must know about a two-dimensional array. So I have explained them. Now let us continue with the other topics in an array. In this video, I'll give you a demonstration for creating two-dimensional arrays. In the previous video, in the whiteboard work, I have shown you what are the methods of creating a two-dimensional array. So just we'll look at those methods and verify them here and see how to do that. In our remaining part of course, wherever we require two-dimensional arrays, we may be using any one of these methods. So let us see the method. The first method I have shown you is we can create an array inside the stack. So a normal method that is provided by the compiler, if you follow that method, an array will be created inside stack. Suppose I want a array with 3 rows and 4 columns. So this is a two-dimensional array of dimensions 3 by 4. If I want to initialize, then every row I should initialize it. So the first row is having values 1 to 4. Second row is having values even numbers. Then third row I will take the values odd numbers. So there are 3 rows and each row is having 4 elements because there are 4 columns. So this is the way we can create a two-dimensional array. This will be created inside stack. Remember this. Then the second method is I can take an array of pointers of size 3. So this 3 is for rows. Now columns are not created. So this array of pointers will be created inside stack. Then to each location in this array, I can create an array in heap and assign it. So for each location, I will create an array inside heap and assign it. Then create an integer array, malloc of size 4 and multiplied by size of an integer. So this is for the first location. Then I have 3 such locations. So I will copy this code and paste it for the remaining locations. This is for 1 and this is for 2. Now this is for 1 and this is for 2. So this is how two-dimensional array is created. Already we have seen the board work for this one. Then the third method I have shown you. For that, I will take a double pointer here, integer double pointer c. in C language, we should declare the variables in the beginning. So I have declared it in the beginning. Now, it's just a double pointer. So first of all, I should create a array for rows. So C assign integer double pointer malloc. It's a size of 3, that is size of integer pointers. So first is an array of pointers. The next is C of 0. I should assign a array from heap. So I should create an array in heap and I should assign it. So array in heap is of size 4 now. So this is for first row. 4 into size of integer. Then same code, I will copy it and use it for rest of the rows. Yes, this is for 1 and this is for 2. See, this first rows itself are created in heap, and the rest of the arrays, 3 arrays, are also created in heap. And here rows were created inside the stack, and these arrays, that is 3 arrays, are created in heap. So that's all. Syntactically, I have shown you how the code works. So I have written the code and all this code is error free. Now one thing we'll do, I will take for loop and I will try to print all these arrays one by one. I will take integer I and j. Using these, I will print the elements of these arrays. Though I have elements only in first array, I don't have elements in second and third array, but just let us print them and see whether it works or it gives an error. So using for loop, I is less than 3, I plus plus, then for j assign 0, j is less than 4 because this is for columns, j plus plus, then printf percentile d a of I comma j. So values from this array will be printed, that is a array that is created inside stack. Now for a new line, I will say printf /n. So after the end of every row, let it take a new line space. Let us run this one. Yes, the values are printed. The values that I have given here, that same values are printed row by row. Now the same for loop, I will cut it from here and paste it after creation of B, and I will print array B. B is not having any elements, but it should get garbage values, but it should not give any error that invalid memory. Yes, it is printing garbage values are printed. Then same 2 for loops, I'll use it for C to verify whether it will allow us to access that memory or not. If the arrays are not created, then it will not allow us to access. This is created using double pointers. So I'm able to access these locations using C of I comma j. Yes, it is working. Some values are zeros and some values are random. So all those values are garbage values only because we have not initialized. That's all. We have seen the methods, how to create two-dimensional array. Just for confirmation, I have written the code. We may be using it if required. That's all in this video. Now let us learn how a compiler handles array or manage array. So what are the issues that it has to deal with? So for explaining that, I will take an example of simple variable, that is scalar variable. See, in our programs, we use variables as names for representing some data. But when compiler converts into machine code will not have variable names. During execution for this variable, let us say 2 bytes of memory is allocated and the addresses are 100 and 101. Suppose during execution this is the memory allocated. This variable x represents this address. And the value 10 has to be stored at that location, means at this address 100. So basically machine code should refer the location with their addresses, not by name. Then compiler has to convert name into an address. When the address can be known, when the memory is allocated. When the memory is allocated during execution. So it means the memory for the variable is allocated at execution, then only the address can be known. Then the how compiler will write down the address at compile time. So that's what we will learn about this issue in array, that is a vector variable. Here we have an example array which is already initialized in my program. Then during execution time, memory will be allocated for the array and the values will be stored in corresponding locations. Assume that these are the addresses. Now in my program, if I have written, I want to access a of 3 and there I want to store the value 10. So it means I want to store the value 10 here. Then this statement in my program has to be converted into machine code, which is referring to this address, that is 206. The address is 206. So compiler has to refer to that location, that is 206. So how this code of our program will get converted into machine code? So actually compiler needs address of a location a of 3. So how it is obtained? So at compile time the address cannot be known. So compiler will write down a formula for obtaining the address. So how that formula looks like, let us see. See, this is the name of an array and this is the first address of an array. So this first address we can call it as L0 or location 0. And the name of an array is called as base address of an array. So any location in an array, index in an array can be accessed with the help of base address. Let us say L0. So L0 is the base address, that is 200. So this is the starting address of an array. Then which index I want to access? This one. Its address is how much? 6. So this address I want to access, that is 3 into 2. This gives me 206. So why 3? This is the index that I want to access. Then why 2? Because each integer takes 2 bytes. 2 bytes. So it means from the base address of an array, location 0, I want to access a third index where each index takes 2 bytes. So the final address will be 206. So using this formula, the address 206 can be obtained. So I will convert that into a formula. This is L0 plus 3 into size of an integer. So address of a of 3 is obtained like this. Now for address of any location a of I, how it can be obtained? L0 plus I into index into. Now this is an example of integer array, so 2 bytes. If it is float array, it may be 4 byte, character array may be 1 byte, double array it may be 8 byte. So depending on the data type, the number of bytes taken by each element may vary. So I have to take the size of the data type. So we use a variable that is W. So this is base address, this is index, and this is size of data type. So this is the formula used by compiler for converting any index to an address. Now for obtaining the actual address during runtime, our program must know the base address of an array. So base address of an array will be updated once the program starts running and once the memory for array is allocated. So the address of this location is known during runtime and it is updated at runtime and it is called as data binding. So if you want to study about this one, you can study about systems programming or assembly language programming. There you can learn about these things. So here we have learned how a compiler generates the formula. So this is a formula for address and this is not actual address. So this is a logical address. And this is not a direct address. This is related to base address. So this is also a relative address. So the formula is a relative formula based on base address of an array. Some compilers allow declaration of an array from starting index 1 also. Then how the formula will change? Let us look at it. I have modified the declaration. Suppose in some XYZ language, an array can have indices starting from 1 to 5. Then this will be index 1 and the last index will be 5. Now, if I want to access any location in an array that is A of 3, this location I want to modify it to 10, then how the formula is written by a compiler. So, for the address of a location A of 3, the base address, that is 200, plus, see, third index is this one, so it has to reach here, that is 204. So it should be 3 minus 1, 1 less, because the indices are starting from 1 onwards, into 2. So this will be 204. So for any index, address can be obtained by A of I is, this is location 0, L0, and this is index I minus 1 into, this is the word size, that is the data type size, that is a W. So this is the formula if the indices are starting from 1 onwards. So this is not there in C, C++, but this used to be there in old languages. They used to allow array declaration from any starting index. So programmer can have an array start from 0 also, 1 also. But in C, C++, it is strictly from 0 only. A reason why? Why in C, C++ we cannot have array indices starting from 1 onwards? Let us see this. We have seen the formula for array indexes starting from 0 also. So just I will recall that formula, that was I into W. And this is index starting from 1 onwards. So this is the formula. So the difference is there is one arithmetic operation extra, that is minus 1 is extra. So if you count the number of operations 1, 2, 3, and here there are only 2 operations. So one operation is extra. So as this is an array, for accessing each location, I have to use the formula. So if there are n location, then this operation will be performed for n times if I am accessing all the locations. So though it's a matter of a single operation, that is just one operation extra, but it will be slower depending on the size of an array. If the size is very large and I am accessing all the elements, then it will be really slow. It will be affecting the time taken by a program. That is the reason C, C++ languages, they allow array indices starting from 0 only, because the formula have just less number of operations and it is faster than this formula. So that's all about single dimension array. Now we will learn about two-dimensional array. Let us see how a two-dimensional array is managed or handled by a compiler. In our program, we declare a two-dimensional array like this. Suppose I am declaring an integer type array of dimensions 3 cross 4, 3 rows and 4 columns. Then this is how 2D array we draw on paper. We visualize that this is how we got a two-dimensional array. Any element we can access with the help of its row number and column number. So this is A of 2, 1. But the reality is, during execution, the actual memory allocated will be linear. It will not be in terms of rows and columns, but it will be like a single dimension array. So total 3, 4, 12 locations are there. So here we will have 12 locations of type whatever you have mentioned here. So it's an integer, so 2 bytes I am taking here. Now these are total 11 location, and assuming that the starting address is 200, so on 2 bytes I have increased, and the last bytes address is 222 and 23. Now the problem is how the elements of two-dimensional array are stored in single dimension array. How the mapping is done. So there are two methods of mapping. First one is row major mapping, and second one is column major mapping. So these are the two representations of a 2D array mapped on a single dimension array. So we call it as row major mapping or row major representation, column major mapping or column major representation. So we'll learn about both. So first let us look at how a row major mapping is done. Let us look at row major mapping. See, we assume that we have a two-dimensional array and the elements are organized like this. but the reality is they are stored in a single dimension array. How they are stored? So they are stored row by row, row by row. So in row major mapping, the elements are stored row by row. So I will copy these elements row by row. So first row elements are A00, 01, 02, 03. So I will write them here. A00, this is the first value in the first row, 01, 02 and 03. So this is row number 0. This is index 0. So I have completed the first row, that whose index is 0. Now I will write down the elements of next row. This is row index 1. Then the last row, A20. So this is row index 2. So that's how the elements of that two-dimensional array are mapped on a single dimension array row by row. So this is row major mapping. Now we need a formula that should be used by a compiler for accessing that two-dimensional array. Let us take one example and frame a formula. Suppose I want to access an element at index A of 1, 2. This is the element. A of 1, 2 is present here. Now in our program we will be writing like this, like say A of 1, 2 I want to store the value 10. Then that A of 1, 2 has to be converted in the form of an address by the compiler. So already we know that the addresses cannot be known at compile time. So compiler writes the formula for obtaining an address. So let us observe what should be the formula. So for getting the address of a location A of 1, 2, this ADD is for address. Now to reach here, that is 1, 2, 1, 2, that is present here. To reach here, the starting address is 200, okay, 200. Then I should leave all the elements of one row, that is row 0. I should leave all these elements. So how many elements are there in a row? 1, 2, 3, 4. That is equal to number of columns. So I should leave 4 elements. Okay, 4 elements I have left. Then 200 is this index. If I leave 4 elements, then 1, 2, 3, 4. So here I was in the beginning of the first row. Now here I am in the beginning of the next row, that is index 1. So here, so from here, how many elements I should move further? 1, 2 elements. So I should move further for 2 elements. Then this should be multiplied by, there are 2 bytes for each element because it's integer. So this is 2. So this is 200 plus 6 into 2, that is 212. Yes, I got the address. So I have just worked out by taking the addresses and the index, and I got the address, that is 212. Now let us try for one more element. Let us take this element 2, 3, A of 2, 3. So address of A of 2, 3. So if you see that A of 2, 3 is at address 222. So I should get this one. Now let us follow the same method. First take base address 200. Then from here I should skip 2 rows. So 2 rows means 2 into 4 elements in each row. See, 4 elements and 4 elements. So I should skip 2 rows. Thus I will be in the beginning of this third row, that is row index 2. So it means earlier this was 1 into 4. Now this is 2 into 4 plus. Once I skip first row, I am here. Then I skip one more row, I am here. That I am skipping 4 elements for each row. Then from here I should move by 1, 2, 3 elements. So that is 3 elements. This whole thing should be multiplied by 2. So how much it gives? This is 4 to 8 plus 3, 11 into 2, 22. So this will be 222. So yes, I got the address. Now from these 2 examples, we are in a position to write a formula for it. So address of any index A of ij, we take I and j for representing the indices. So this is L0 plus, L0 is the starting address, that is the base address, L0, location 0, plus this is I into number of columns. So let us call this as M cross N. So this is N plus this one is 3, third element. So that is J. And this whole thing multiplied by W. So this is the row major formula used by compilers for obtaining the address of elements of two-dimensional array. Two-dimensional arrays are accessed using two indices, but actually they are kept in a single dimension array which needs just one index or the address. So the address is obtained like this. So this is about row major. Now one more thing. See, if a language is allowing indices starting from 1 onwards, then how the formula looks like. So I'll just remove this and show you here. If a language is allowing indices from A of 1 to 3 and 1 to 4, I will not work out everything. Directly I will write on the formula. So the address of any location A of ij can be obtained by L0 plus. See, already we have seen it for single dimension. This I minus 1 was used because the indices are starting from 1 onward. So here it will be I minus 1 into N plus J minus 1 also, then multiplied by word size, that is the data type size. So this is the formula. See, in C++, array indices starts from 0 only. So C++ uses this formula. C language and C++ language follows row major representation and they use this formula. But if any language is allowing indices from 1 onwards, then it has to use this formula. Now when it comes to two dimension, let us count the number of operations done. 1, 2, 3, 4. And here 1, 2, 3, 4, 5, 6. So 2 extra arithmetic operations are performed. So this formula will be little slower or costly in terms of time. If you have many elements and the dimensions are very large, then accessing all the elements will be very time consuming using this formula. So that is the reason the languages like C++, they start indices from 0 only. They allow indices only from 0 onwards, so that the formula is little simpler than the other formula. Now next, let us frame a formula for column major mapping. For column major mapping, the elements of this two-dimensional array are mapped on a single dimension array column by column. So I will fill these elements column by column. These elements I will take. So first column are A 0 0, 1 0 and 2 0. So first column elements are A 0 0, 1 0, 2 0. This is column index 0. Then this is column index 1. These elements. So I have finished with these elements. Now these elements. The next column A of 0 2. This is column 2. Then A of, this is column 3. So the elements of a two-dimensional array are mapped column by column. Now we need a formula for obtaining an address of any element. So this address, I have taken the addresses starting from 200 and as integer, every integer takes 2 bytes. So this is 200 and 201, 202 and 203, 204 and 5, so on. Then let us call this starting address as L0, that is base address, location 0. Now let us take some example element from there and frame a formula. Suppose I want this element 1, 2. See, where is 1, 2? Here. It is in column number 2. So address of A of 1, 2. This is base address, that is 200 plus. Now for reaching this element, I should skip first column and the second column. 2 columns I should skip. So 2 into, how many elements are there in each column? 1, 2, 3, 1, 2, 3. So columns are having 3 elements. So that is equal to the number of rows, M, that is 3. So 3, then plus. Once I have skipped column 0, I am here. Then I have skipped column 1, I am here. Now from here, how much I should move? Just one element, So you can see that this is 2, 1. So this is 2, 1. And this has to be multiplied with number of elements that are W. So this will be 3 to 6 plus 1, 7 into 2, 14. So this is 214. And you can see that the index of A of 1 comma 2 is 214. So that's how we got the address of a given element. Now let us take one more element, that is A of 2 comma 2. Now let us take one more element, that is A of 1 comma 3. 1 comma 3 is here. So how to get the address of that one? So the address of A of 1 comma 3 is 200 plus. Now I have to skip how many columns? I should go in third column. So skip 0th column, first column and second column. So I have to skip 3 columns, and in each column how many elements are there? These are 3 elements. So this is 3 into 3 plus. Now once I reach here, how many elements I should move forward? Just one element. So this is multiplied by 2, and this is 339 plus 1, 10 into 2, that is 20, 220. So 220, this is the address. Yes, 220. The element is here. This A of 1 comma 3 is here. So now we have 2 examples. We can prepare a formula. So let us prepare a formula for any index A of ij. This is location 0, that is base address L0, plus this is 3 and 1 or 2 and 1. See, 2, 1, 3, 1 are used. So this means first j, then I. So this is j into number of elements in a row, that is 3. Number of elements in a column, that is equal to number of rows, 3. So this is m, plus 1 is taken at the last, so this is I, that is row number. This is multiplied by W. So this is the formula for column measure representation or column measure mapping. I will write down row measure mapping formula also just below this one, so that we can see the difference between them. This was row measure formula L0 plus I into N plus J multiplied by W. So in row measure, I was used first, then J, but in column measure, J is used first, then I. So I can say that in row measure, we go from left to right, and in column measure, we go from right to left. So first J, then I. So first J, then I. In row measure, first I, then J. So this is for row measure, and this is for column measure. Now let us observe one more thing here. See, these 2 formulas, how many operations they are having? Plus, plus, multiply, multiply, plus, plus, multiply, multiply. So both the formulas are having same number of operations. So in terms of time, both are equally efficient. So a compiler may follow row measure mapping, or it may follow column measure mapping. So if you are designing your own compiler, then you have option to select any one. Both are equally efficient. There is no difference in them. We can't say one formula is better than another in any situation. But C++ follows row measure formula. This one, they follow row measure formula. So that's all about So that's all about 2-dimensional array. We have discussed how row measure and column measure mapping is done, and we have seen the formula for index starting from 0, and also we have seen the formula for indices starting from 1 also for row measure. Now for column measure, you can devise the formula. So you know well that only I minus 1 and j minus 1, minus 1 has to be taken. Then we get the formula for indices starting from 1 onwards. So that's all in this topic. Let us prepare a row measure formula and column measure formula for 4-dimension array. I'll show you the approach. Then using same approach, we will see a row measure, column measure formula for 3-dimensional array also. So here already I have an example of a 4-dimension array. Array name is A, data type is something, and the dimensions are D1, D2, D3 and D4. Now for the address of any location whose indices are I1, I2, I3, I4, then what should be the formula? So let me prepare the formula for row measure. In 2-dimensional arrays, already I have explained that row measure is done from left to right and column measure is from right to left. So we will go from left to right. So let us take, first is I1, the first index, into multiplied by, leaving first dimension, multiply rest of all the dimensions. So this is a D2 into D3 into D4. Now second index, that is I2. I2 is multiplied by, after dimension 2, all the dimensions should be multiplied. So this is a D3 into D4, dimension 3 and dimension 4. The next is index 3, I3. So the third index, I3, after third index. So after third dimension, all dimensions should be multiplied. So only D4 is there. Then plus, last I4, fourth index. After fourth dimension, everything should be multiplied. So nothing is there. So multiplied by W. This is the formula for row measure mapping of a 4-dimension array. So you might have observed what is the procedure for preparing the formula. So for every index, we take the dimensions after those dimensions. For I2, we take all the dimensions after D2. So this is the approach. We have taken it from left to right. Now I will write the formula for column measure. Column measure formula, address of, now for column measure, already I said that for row measure we go from left to right. For column measure, we go from right to left. So let us prepare the formula. L0 plus, first one is index 4. So I4 multiplied by, see, this is dimension 4. So take all those dimensions before dimension 4. So D1, D2, D3. D1 into D2 into D3 plus. Now this one, we are moving from right to left. So next is I3, index 3. So go to dimension 3 and take all the dimensions before dimension 3. So this is D1 and D2. So multiplied by D1 and D2 plus I2. I2 multiplied by, go to dimension D2 and take all the dimensions before that. So that is D1 plus, this is I1 multiplied by W. So that's it. This is the approach for preparing the formula. Using 4 dimension, I have shown you how to write row measure formula and how to write column measure formula. Now using the same approach, we can write the formula for any dimensions, any number of dimensions. So even 2D was following the same approach, but this is a very small problem. So we have seen it thoroughly with the diagrams and everything. But here I am showing you directly the formula. Now based on this formula, by observing this one, we can prepare a general form of this one for n dimensions. So let us prepare a general formula for n dimensions for row measure mapping. So I am showing it for row measure mapping. Let us take same formula. I will generalize it for n dimensions. L0 plus, see, all these terms are added. See, this is one term, then next this is the term, next this is the term, next this term. So total 4 terms are there, 4 terms are added. So for addition, we use sigma. And here I1, I2, I3 and I4 is used. So I and its subscript, that is I1, I2, I3. So I will call it as P. So P takes the values from 1 to, it is going up to 4. So instead of 4, just make it n. So this will be for n dimensions. So P takes the values from 1 to n, so for n dimensions. So this will become I1, I2, I3, I4 and so on up to n dimension. Next thing, every index is multiplied by dimensions. This I2 is multiplied by D3 and D4. So it is multiplied by product of dimensions. So this is a product of dimensions, product of dimensions. So product of pi we can use of D. Now these dimensions are taking subscript from 2, 3, 4. So this is just 3, 4. So whatever I is, this is 1. So this is 2, 3, 4. So this is taking the values after P. So this is DQ and Q takes the values from P plus 1 to N. So it is going from 2 to 4, 3 to 4. So this is 2, so 3 to 4. This is 3, so 4 to 4. So Q takes the values from P plus 1 to 4. And this whole thing should be multiplied with W. So this is the row major formula and general form of n dimension. So similarly, you can prepare a formula for column major mapping for n dimensions. So try this formula by yourself. Now let us do some analysis on this one. I'll remove this column major formula and we'll do analysis on row major formula. Let us see how many multiplications are performed for getting this result. Let us count them. 1, 2, 3. 3 multiplications here. 1, 2. 2 multiplications here. And 1 multiplication here. Then that W is common always. That is plus 1. Depending on dimensions, the number of multiplications inside the brackets may vary. Now for 4 dimensions, how many multiplications are there? This is 3 plus 2 plus 1 for 4D. It means for 5D, how many multiplications will be there? So 4 plus 3 plus 2 plus 1. So for n dimensions, how many multiplications will be there? N minus 1 plus n minus 2 plus goes on to 3 plus 2 plus 1. So this is nothing but n into n minus 1 by 2. So n into n minus 1 by 2 is n square multiplications. Oh, these are too many multiplications. So the time taken for evaluation of this formula is n square multiplication operations. So this is too much time consuming. So the row major formula used by the compilers take order of n square time. So is there any way to reduce the number of multiplications? Let us see what we can do for reducing the number of multiplications. I will take only the portion of formula that is inside the brackets and I will write the formula from right towards left. This is the row major formula. I am just writing it reverse. So this is I4 plus I3 into D4 plus I2 into D3 into D4 plus I1 into D2 into D3 into D4. So I have taken only the portion of the formula that is inside the brackets and I have written from the last term onwards so that we can reduce the number of multiplications. So if you observe, this is having 4 values multiplied, 3 values multiplied, 2 values, and then there is no multiplication. So I have taken from the smaller value onwards. So first is smaller, then go on increasing. Now in this, if you observe, this I4 is as it is plus D4, D4, D4. D4 is common among all these terms. So I can write D4 multiplied by, D4 is common, so I3 plus I2 into D4 is taken as common, so D3 is there, plus I1. D4 is taken as common, so this is D2 and D3. Okay, so I have taken common. So I got one multiplication here. Let us continue and see if we can take more common values. I3 plus. Now in these two terms, D3 is common. So I will write down D3 multiplied by and I2 plus I1 into D2. So I have taken D4 common and D3 common. Now only two terms are remaining here. Further, I cannot take anything common. This formula can be rewritten like this by taking dimensions as common. Now this is the same thing what is there inside the brackets. So let us see how many multiplications are there. This is 1, 2 multiplications, 3 multiplications. Oh, so for 4 dimensions, just there are 3 multiplications. For 4D, 3 multiplications are there. And for 5D, there will be 4 multiplications. So for ND, there will be n minus 1 multiplication. So total time for performing multiplications will be order of n. So this formula reduces the number of multiplication from n square to order of n. So by taking common, I have reduced the number of multiplications. So this is how we can reduce the number of multiplication in row measure as well as in column measure formula. So the rule that we have applied, that is taking commons to reduce the number of multiplication, this rule is called as Horner's rule. So we have applied Horner's rule to reduce the number of multiplications. So that's all with 4 dimension to n dimensions. Now let us prepare row measure and column measure formula for 3-dimensional array. We have already seen formulas for 2 dimension, then I have shown you a general method by taking 4 dimension. Now using the same general method, we will prepare a row measure formula and column measure formula for 3-dimension array. So here I have an example of 3-dimension array whose dimensions are L, M, N, N. Then let us prepare a row measure formula for an element at index I, J, K. So indices are I, J and K. So let us prepare a formula. L0 plus, that is the base address. So I am not drawing a diagram showing you 3-dimensional array. As you know the approach for preparing the formula, same thing will follow. So let us take indices I. This is for the first dimension. So multiply remaining other dimension. So I into M into N plus second dimension, that is J into, so J is for second dimension, so multiplied by third dimension, that is N plus K, and this was the last dimension, so multiplied by W. So K is the last index. So we have prepared a formula by moving from left to right. Now similarly, let us prepare a formula for column measure representation. So for column measure representation or column measure mapping, address of A of I, J and K, this is, we will prepare the formula by moving from right to left. So this is L0 plus, first take K. K multiplied by, K is for last dimension, so multiply with M and L. So LM we will write L into M. Plus, next index is J. So J multiplied by, J is for second dimension, so take L. Then plus I multiplied by W. That's all. This is a row measure and column. This is a column measure formula for 3-dimension array. So I have used the approach that I have shown you for n dimension, and I have directly prepared the formula. Now, one of the things that mostly confuses the student, that is, see, if I have a 2-dimensional array of dimension m, n, then we say row measure means first row then column, column measure means first column then row. Then if suppose we have 3 dimensions, then what? Row measure means what? So already I have explained this one, that row measure means go from left to right and column measure means go from right to left. Don't say first column then row, because there are 3 dimensions. So if this is row, this is column, then what is this? So instead of giving a name, let us avoid giving any name to that one. Let us say for row measure left to right, for column measure right to left. So that's all about 3-dimension formula.